So OSV, what's OSV? So OSV is a new operating system. It's a rise from scratch. We're using our own kernel. We started from zero. So it's a new operating system, and the idea is to design a new OS targeted for virtual machines in the cloud and running Web 2.0 workloads. So we're talking about web scale, NoSQL, web servers, Tomcat, Nginx, Hadoop, whatever. So that's our goal is. And just to repeat that, because sometimes cloud operating system is an overload term. So I'll be very, very specific. So here, OSV is in the orange box. That means that we're running on top of a hypervisor. It's a commodity hypervisor, and we do nothing in the hypervisor level. So we're running on VMware, KVM, Zen, and even VirtualBox, because we'd like to be developer friendly, so you can run OSV on your own laptops. And on top of us, there's the unmodified applications. So that's a use case for OSV, and it's good for public cloud, private cloud, your data center, etc. So it's a really, really hard task to develop a new operating system. We get to find it every day, although we're pretty much experienced with this term. The founding team, myself, and Avi Kiviti were the ones that developed the KVM hypervisor from scratch through the 7-8 years of development at a startup called Kubernetes and later on at Red Hat. And we're highly familiar with virtualization and the Linux operating system, which is great, but it's general one. And here we're trying to develop a new operating system that will target the workload that I described before. Thanks. It's a relatively young project. It's 1.5 years on the road. We're pre-beta. After alpha, we have Cassandra working on top of an OSV on AWS or Google Compute for over a year. And we're thinking that towards the end of the year, we'll be ready for beta. We're 18 people across 9 countries. And why 9 countries? Because from the very get-go, we wanted to be open source, and we optimized to hire the best brains in the universe instead of those that just live next to me. So that's the idea with the experience in KVM, Zen, and even containers here, Glauber. So besides of writing code that doesn't suck, we want to write the code that really runs your application fast, and in this case, Cassandra. So without further ado, let's see a demo of OSV.
All right, so the demo that I'm about to show you is going to be starting up a complete first-class virtual machine. So we're not starting a container. This is actually just a full boot. OSV is going to start up. It's going to obtain its IP address from the hypervisor, and it's going to start Memcached. So let me just run it from our handy run tool for developers. OSV is booting. It got its IP address, and Memcached is running. That was a complete boot. All right, let's take a look at another virtual machine image.
It was too fast. Let me time it. Are you sure you empowered the hypervisor and the OS? And did it all run?
The whole thing ran. Yes, that was the hypervisor starting up a new virtual machine, the OS booting, getting its IP address, so it's on the network, and starting a real NoSQL application. So let's start an application that's a little more complicated. Let's do Redis. There we go. OSV starts up. It reports its version here. OSV starts up. It reports its version, gets its IP address, launches Redis, and Redis is ready to accept connections. Did you time that, Dor?
No, it was too fast, but I rely on you.
All right. So let's do one more. And this is one that might be familiar to people around here. This is Cassandra. OSV just started. And we had a crash, all right. Let me kill it off. It has not done that. I've practiced this demo like 15 times. Let me start it up again.
Isn't this our debug demo?
All right. Let me go back to this again. Kill it off.
I think the ZFS is complaining, and I think we have a corruption in that particular image.
All right.
But you can get it. Let's give it one last shot, but
Yes.
you have a corruption in the ZFS. But, well, we're prepared for that, and that's why I had Don to do the demo and not myself, because you can build it in the background while I'll continue with the presentation.
Yep. And we're actually just able to integrate the boot of, we're able to integrate the build of a complete application with the build of the OS. So I'm going to start the make.
That's fine. Don't be shy.
All right.
All right. So 2 out of 3, I call it a success. But really, that's super weird. But yeah, we're going slow and steady with the development, and we're pre-beta. You've seen a fast boot, but OSV isn't just about fast boot. So let me explain a bit and dive into the architecture. So on the right-hand side, you see a traditional stack with regular OS, like Linux, probably. Windows is out of the picture. Thank you, Microsoft, for sponsoring the conference. You did your share. So afterwards, the OSV architecture is about being as slim as possible. Sometimes this architecture is called library OS. So basically, when we run a standard C applications, we're just linking with the application in the same address space. So OSV is all about performance and to be thin without extra baggage. So we use one address space, one process with multiple threads and SMP and performance, but it's all living within the application space. And the application doesn't need to be rewritten. If it's a shared library, it's linked together with our kernel, and that's it. With standard Linux tool and all that, like the thing that we compile Cassandra with. In the case of high-level code, like a JVM, Ruby node, then it's run on top of OSV, again, unmodified, and the whole stack is slimmer and thinner. So that's one of the secret sauce behind the OSV features. So you probably ask, what is it for me? What's the value proposition? So it's twofold in the case of OSV. One is performance, and not just boot, so it's throughput and latency. And the second is manageability. So let me start with performance. Who cares about performance? Do you care about Cassandra performance? Just to make sure, because Cassandra rocks, and each time you just add more SSDs as if they're our chip, and that's it. But if you do care about performance and throughput and latency, it's more than the disks, and we're trying to do our best. So first, with Memcached, here's the performance of traditional Linux VM. That's here around 100,000 transactions for the particular hardware that we had. When we ran OSV with Memcached unmodified, we got around 40% improvement. It was here. But then we saw what can be done. We figured out that Memcached isn't a well-written application. It's not totally in the far edge, not sophisticated as Cassandra. And it had lots of cache contentions and lock contentions. So we chose to rewrite Cassandra from scratch. And that's the performance we got when we wrote Cassandra using our own kernel APIs. Wrote Memcached. We couldn't just rewrite Cassandra that fast. So Memcached is simple, and we use our own kernel APIs that are approachable for the application, and that's how we manage to get this performance that are actually faster than a physical host.
So does it need to be run on your operating system? What about the same improvements were made on Linux? Wouldn't that improve performance as well?
So certainly Memcached, stock Memcached isn't that good, and you can improve that over traditional OS. But then you'll need to write kernel mode code, and that's more complex, and not everything is still approachable even from the kernel layer, so it's more difficult. In addition to that, I'll soon show that we have specific advantages in our architecture that you can't do it on Linux just like that, even if you're willing to write kernel code. Next example is Redis on Vitamins. So OSV is here, and Linux Ubuntu is up to here. It's about 80% improvement on most of the Redis operations. This is unmodified Redis. Memcached was a nice attempt, but we're not just trying to rewrite all of the applications in the world. So that's the performance we got with Redis. In the past several months, we started to optimize the Cassandra use case, which is really far more complex than that. And I'm happy to say that we started to get better results than what are achievable on Linux. So on the best Linux, we chose CentOS, which is more performing than some other distribution, although it's surprising, because they're all derivative of the same Linux kernel. So that's the performance we get. We get around 15%, 20% better than Linux today, and we won't going to stop here. We still have idle time, while Linux doesn't have. We're trying to figure out what can be done better, whether it's scheduling improvements that we can do or better caching. So it's keep calm, and work is in progress. It's a good question. I think it's in time, and it's read. I think
Those are reads.
yeah, but everything is read.
No, the first one is insert, and then it's a sequence of reads. And we could have taken out the first ones, but we decided to keep them all because you can see here that we do have a problem when the JVM is compiling the code. So this is a sequence of reads over time. And it takes us a little bit more time to achieve peak when the code, the JVM is still compiling, but when we do peak, we're better.
It's Cassandra stressed, standard one. Okay. So beyond linking with the application, we're trying basically every trick in the book in order to get the best performance possible, and also out of the box. That's really one major factor and consideration that we're trying to get, because there are so many knobs in Linux that are really, really hard to control. And in our case, we're just trying to be performing as much as possible just like that in auto-tune parameters. So we use the former speaker from eBay mentioned huge pages. Our system is designed from the very beginning to use huge pages. Normally they're good for long-running processes, both in the JVM and also virtual machines. In virtual machines, it's even more important because there are double layering of page tables. We have unique ability to move pages from the heap to the system and vice versa. So we apply memory dynamically to where it's needed. If it takes a lot of while to tune the JVM heap size correctly, sometimes if you put too small of a heap, then you'll suffer from no memory and a lot of GCs. If the memory is too big, then you may not have enough memory for the page cache, or each GC you're going to have long stop the wall. So we dynamically steal pages from the Java heap and apply it to where it's needed, either the socket layer or the page cache. With I/O, we're starting to do zero copy, and I'll demonstrate our TCP/IP implementation. With scheduling, for instance, this is an OS that doesn't do spin lock. We just do lock-free mutexes, and the reason is that hypervisor can steal the CPU under your fit, and that's a problem when you use spin lock. The other virtual CPUs will spin for nothing, unlike a traditional physical case. So this OS is designed for this particular case. We have time. So TCP/IP. Basically, we embrace one of the designs done by Don Jacobson, one of the TCP/IP inventors. So back in 2006, he sort of woke up this morning and he discovered that the TCP/IP stack was designed in the 80s where there was only a single core. And back in 2006, multi-core era arrived, and it wasn't efficient because the TCP/IP processing is done first by the interrupt, and that schedules the software interrupt, and afterwards the socket layer processes the TCP/IP packets themselves, and afterwards it reaches the application. The problem with multi-core is if all of these ellipses will be run by a different core each time, then everybody will try to lock the same data. So you're going to have lock contention, and also data will bounce from one core to the other, and you'll get cache contention as well. So his design was about to take the TCP/IP out of the kernel and glue it together with user space, like this one. So here, the kernel basically just identify the connection using the tuples and make the selections, and the TCP/IP processing is done in the context of the application threads. So it allows a maximum parallelism and minimal data movement. And he got between 50% and 100% improvement in throughput and latency. So for us, it was perfect because we already are living in the same address space. We did need to change our TCP implementation a lot in order to eliminate various locks and let it be scheduled in the same entity together with the application. But today, we're receiving 70% better latency than Linux and 30% better throughput. So it's really helped our design. Okay. So not everything is about performance, although I can go on with performance much more. Manageability is just as important, sometimes even more. And by manageability, I'm talking about various aspects. It's about upgrade. It's about configuration management. It's about tweaking and tracing and debuggability. So we're trying to address that with our OS as well. Who's familiar with this Linux tracing taxonomy? It's really cool, by the way. Who knows all of the tools that are listed here? Most. Well, so again, Linux is a fantastic system, but you need to be a rocket scientist in order to control it. And even even if you are a rocket scientist, there are so many inputs that it makes really, really difficult to control. So we're trying to address this scenario as well as some others, and we'll present that. So let's go to our management interface. Remember, it's a beta that it's crashed before, and the combination managed to pass. So I think Don deserves a big clap. So we're booting Cassandra, and now it's booted just fine.
The OSV boot was just those first two lines, and then now it's just Cassandra starting up. And I'm just going to run a little script in another window to create a little traffic so that when our graphs populate, we will get some data. All right, you'll see that we have a nice web interface with different tabs, and we can switch between them, and one of those is going to light up as the Cassandra tab.
Yeah, I think we lost it, the Cassandra tab.
We did not lose the Cassandra tab. The Cassandra tab was just here. The the browser's still loading. The Cassandra tab's going to light up in a second. In our main tab, this is some of the stuff that's over on the right side in that Linux profiling tab. For OSV, we've got everything, all the fundamental stuff organized, how much memory is being used, CPU usage, all your basic stuff that would show up in your management tools right here. And this is actually not just a nice looking web interface, but it is also available through a REST API. So if you know curl, you can get any piece of information off of the system. You don't have to remember which of the performance measuring tools you use to get a certain piece of information. You can get it all in one place from one API. And that's nicely self-documented. We switch over here, we can see the threads on the system. Let me reload just to get our Cassandra tab back. And this is showing all the threads that are going on, mostly as you'd expect to see on a running Cassandra instance, a lot of them. The profile is really interesting. The profile lets you check the status of any trace point on here. So let's see, TCP state. We can watch our TCP and TCP input ACK. This is a good one. You can see the rate of ACK packets that's being sent out over our TCP. And let me hit reload just one more time to see if we get our Cassandra tab back.
I think that our new, tried out, but I tested our new release on AWS, and the Cassandra tab was gone, and we have a JVM tab. It was gone too. Someone stole it overnight.
I never get pulled during a conference.
So if it doesn't, if it's not here, then it's just someone stole it, and you know, we'll go into GitHub and find the blame.
Okay.
Never mind.
All right.
Let's get back to the presentation. Maybe we have, oh, here you can see we do have a JVM tab and Cassandra tab. In the JVM tab, you can browse, we use Jolokia to translate beans into REST API. So we can browse any data on the JVM. And also we have a specific JVM tab. We have a specific Cassandra tab, which is not visible here. It's a screenshot that I arranged just in case someone will steal our tab. But the idea is that we have a unified single GUI that allows you to check the kernel, the JVM, and the application, whatever it is. And it's all configurable. And every source for the data source for this graph is approachable through our REST API, so you can hook it into your system. Because we think that as much as this initial GUI that we've done is nice, then people want to use the data and read it on their own system, and we can't just do it all. We're trying to just do a perfect Node OS and not rule the world.
So everything you can get to from JMX, there's a REST URL for it.
Okay, beyond performance and tracing, we do some other things. And the main consideration is to have a stateless root file system. Just in general, we started the OS from scratch, but we did took and embrace an existing file system. We embraced the ZFS file system. And why? For two reasons. First, ZFS is a really cool and good file system. And second, they say it takes 10 years to stabilize a file system. We're a startup, so we thought let's just move 10 years into the future. But we have ZFS for your data partitions. And it also runs our root file system. But the idea is to keep the file system as stateless as possible. Everything is built upon REST APIs, and we have 0 configuration file. 0. No /etc, nothing. And the idea is to keep it outside. So the root file system will be stateless, and each time you upgrade it, basically you're going to create a whole new image that will bundle the application and the OS together. So if you have a new OS version or a new application version, just spin off a new instance immediately. It boots under a second, and that's it. And we pull the configuration from Cloud Init that exists on AWS, on Google, on OpenStack, and we were developing something for the data center that will be independent as well. So we have a really good tool to create those images. It's called Capson. Actually, it was inspired by the Docker project. Basically, you can look at Capson as what Docker is to container, Capson is to virtual machines. This Capson file describes how an image looks like. Again, it's pretty much resembles the Docker design, written in Go, and for every application, someone can create a Capson file that basically says, use this base image, in this case, OSV plus a JDK. Use this command line to run your application. That's a command line to run Cassandra with all the standard JVM parameters. It's too long, so I chopped a few. How to make it, that's your own build file. And there is one last thing. What are the files that the output expects to merge while an image is created? So building such an image takes no time, few seconds, depending on the size of it. We can create images that are 20 megabytes inside, like the whole image, unlike like traditional OS that weighs at least 1 gigabyte and beyond that. So it's really, really thin. And also, in order to execute it, it works on every laptop. We use VirtualBox and VMware on Microsoft and OS X. And Linux works great as well with any hypervisor too. And it's the same command line, like capson run, capson build, and that's it for any of your appliances. The next thing is, once you build an appliance, the next thing is to deploy and to manage it. So I mentioned before the Cloud Init mechanism, and the idea there is to put all of the state external from the image. So each time you boot, it will get automatically configured, and we love automation a lot. So basically, once you have this behavior, then you get full stateless, and there's no requirement to run Puppet and Chef because you do everything from the outside. Although we do want to add Puppet and Chef agents, because if you already have a Chef installation, for instance, then we do not want to change the way you install things. But that's the house recommendation. So that's an example. This is a standard Cassandra topology. So there's a section for the application to do whatever. Here, that's standard unmodified Cassandra section. And there's also a section for our own OS where you can put whatever you want in the configuration file or within the Cassandra configuration file, put encryption on top of our REST API server, etc., etc.
So we need to install this software, right?
I'm sorry?
Do we install this software on the Linux?
The Cloud Init?
Yeah.
Usually it just comes with Amazon or Google Compute Engine or OpenStack. And we develop independent server for Cloud Init that exists with those vendors that you'll be able to run locally.
So it's with OpenStack, right?
Yeah, with OpenStack, it's just there.
So that means if we use yours, we don't need a Puppet.
so you do not have to use Puppet. It's possible to use Puppet. Actually, not right now, but that's a plan. But definitely better not use Puppet because this is a file that you can automatically create and use also parameters within this file.
So that means we can use your file to do deployment automation.
Yeah, it's possible to use that. Again, we're trying to confine ourselves and do minimal changes. So the OS will be drop-in replacement to replace Linux or whatever OS that you have over there without changing the environment. So that's why we picked Cloud Init. There are some additional goodies that I'm not sure we have the time. Maybe we do. Let's see if nice thing about platform as a service approach, we're working on a version that will allow you to just allow you as a developer to define a jar or what Ruby file or whatever. If in the future we'd like to support Go, and automatically create an image that will contain this jar. So you'll have just one jar, and that everything that you're going to need to define for the virtual machine. And once we've done that, then it'll be possible to have a base OSV image, and you'll just dynamically throw on it your application as a jar or as a C file, etc., and it will work as you pre-created that. So to simplify the deployment scenario, so to have ongoing scenarios, we already have New Relic integration, which was super cool, and also in order to make it prepared for a really data center design where you have, or also a cloud design, if I may say, you already have centralized logs. So the idea is on Cloud Init, you'll define your log servers, and every instance will send those logs externally. So this particular OS is really designed to just run your workload and to do minimal things while you automate the entire infrastructure. So if I'll summarize, our performance can be really, really good. The more your application is optimized, the better we can provide you, especially if you do a lot of IOs, whether it's a network processing or disk related. We do fantastically well with TCP/IP. ZFS by itself has sophisticated cache replaces mechanisms. It manages recently used pages and together with most recently used, and it makes it what we call scan resist, where if your workload fits the memory, but in parallel you run a low priority batch processing on most Linux distributions that are out there, the batch processing will kick out the real workloads from the cache. And ZFS is really, really mature and handles this really, really well. It runs on any machine and contains the REST API, and we use the multi-tenancy of the hypervisor. So we reuse that, and the images are super small.
And is this on the formal production release?
I'm sorry?
Is this on the formal production release?
Formal protection release?
Release.
It's pre-beta, so.
Pre-beta.
Mm-hmm. So it's open source. So if you can download everything from here and GitHub, and we have Amazon images and Google images, and we also have a Twitter account that needs help since we're a startup and a young open source project. So you're welcome to tweet it, and that's it. Feel free to ask any questions.